the very nice presentation by Professor Marugan, I will try to show you something more applied. Okay? It's how to design a photochemical reactor. But first, let's remind the definition of advanced oxidation process, and that only photophantom and heterogeneous photocatalysis can be driven by the sunlight. Okay? So, as I work in a solar research center, I will speak about sun, the use of sun for photocatalysis, in this case, photophantom. So, this talk will be an applied talk about the design of a solar photophantom reactor. First, let's think about some very important questions. First, the dependence of pH of the photophantom process. The best pH is the acidic pH, 2.8, because it's the optimal. At this pH, we have ion in solution. The absorption of ferric ion, it's the best. And we have no presence of bicarbonate, hydroxyl radical scavenger. But as pointed out by Professor Manato, there is a need to work a neutral pH, especially to treat urban effluents as tertiary treatments. And a neutral pH, we have two main problems: ion precipitation and the presence of bicarbonates. To solve the problem of precipitation, the use of complexing agents has been proposed, and among the different complexing agents, the best one is the EDDS. Now, let's pay attention to some factors to consider when designing a photophantom reactor in this case. First, the inputs. So, what is now before the design? Of course, the availability of radiation. Then, the operating pH. It's not the same to work at acidic or neutral pH. In this case, we will speak about neutral pH. We need to know the reactant concentration, ion and H2O2 concentration, and of course, the wastewater to be treated. And what is the objective of this treatment? That is the decontamination of water. What we need to calculate to design a photochemical reactor, a photophantom reactor, we need to calculate the solar collector surface. Of course, we will need to this end first to calculate the reaction time. We need to know the reactant consumption, and summing up the three parameters, the cost of the treatment. The most popular reactors for photophantom process is the tubular reactor with compound parabolic collectors, known as CPCs. The main feature are that they use commonly a 5 centimeter diameter tubular loop. The tubes are evenly illuminated, but they have a very low ratio between the illuminated volume to the surface of the reactor, around 10 liters per square meter. A new proposal in the last few years is the use of Raceway pump reactors. This is a very cheap reactor. They consist of channels where the liquid is set in motion by a pedal wheel, but the main characteristic is that the liquid depth can be varied easily. So we can use different reactors or the same reactors with different liquid depth. And the ratio between illuminated volume to the surface ratio change with liquid depth. That is, for instance, for 5 centimeters is 50 liters per square meter. For 15 centimeter liquid depth, 150 liters per square meter. Now, let's speak about the impact of pollutant concentration. This is very, very, very important when speaking about photophantom process. When we are dealing with highly polluted effluents, that is the case of toxic wastewater or industrial wastewater, the aim of the treatment is commonly the mineralization of the organic matter, along with the enhancement of biodegradability, because the complete mineralization is not possible. Okay? To reach this goal, we have a great need for hydroxy radicals, and consequently, we use high concentration of iron, typically 20 milligram per liter, and hydrogen peroxide. It's the oxidant agent which gives rise to the hydroxy radicals, around 1,000 milligrams per liter. As we treat a small volume of water, in industrial water, we can work at acidic pH. The treatment times is measured in hours, and we're working with high concentration of the light absorbing species. Normally, we work under irradiance limitation. A different picture is observed when treating effluents containing microcontaminants, very low concentration of contaminants. It's typically in urban wastewater, where the concentration range is in the nanogram or microgram per liter. In this case, we change the aim of the treatment. We don't want the mineralization. We only want the parent compound removal, the micropollutant removal. And in this case, we need to check the removal of chronic toxicity associated to the microcontaminants. As the concentration of contaminants is very low, we have a low need of hydroxy radicals, and we use low concentration of iron and hydrogen peroxide, typically 5 milligrams per liter or between 30 and 50 milligrams per liter. In this case, urban wastewater, we want to treat large volume of water, and we need to work at neutral pH to avoid the cost of pH conditioning. Normally, in this case, the treatment time is measured in minutes, and because we use low concentration of the light absorbing species, we needed to check if we work under irradiance limitation of an excess of light. It's important to take into account how to quantify the effect of radiation on the photophantom process. We normally use two parameters. It's very common in the literature. The T30 watts, it's a normalized time, a normalized illumination time. You know all what it means, as well as the QUV, the accumulated solar energy in the system. Okay? These very common parameters. But these parameters are used for different solar reactors, regardless of the concept design, stir tank or tubular reactors. But they do not take into account the reactor geometry, only the light reaching the reactor surface. To take into account the reactor geometry, we need to use, to take into account the photon absorption. Okay? In this case, the concept of volumetric rate of photon absorption combine the effects of the absorbing species, the ion, the irradiance, the optical properties of the solution, okay, and the liquid depth, that is, the light path length or the geometry of the reactor. Okay? So, in the case study I will present now, we will work about solar photophantom and neutral pH for micropollutant removal, okay, and toxicity removal, because it's a very effective system. The first step for modeling, as very well presented by Professor Marugan, is the modeling of the kinetics. We need to know the kinetics of the system. And to this end, the first step is to work at lab scale. In this case study, we started with a synthetic secondary effluent with a model micropollutant, acetamiprid, at a concentration of 100 micrograms per liter, with 0.1 millimolar of the complex iron-3 EDDS to work at neutral pH, and 0.88 millimolar of hydrogen peroxide. And the experiments were carried out in a solar simulator in stir-tank reactors with different liquid depths, 5 and 15 centimeters. Here I present the results of acetamiprid degradation and the photodecomposition of the iron-3 DDS complex for experiments at 5 centimeters for different irradiances. What do we see in these figures? First, as for the phenomenology of the process, if we increase irradiance from 10 to 40 watts per square meter, we have an increase in the reaction rate, okay? In this case, the system is photolimited. But when we increase irradiance from 40 to 50 watts per square meter, we obtain the same reaction rate. So we have an excess of light, photosaturation. The same phenomenology was observed for the decomposition of the complex iron-3 EDDS. Okay, so this phenomena should be taken into account in the modeling process. In this figure, the effect of limitation or saturation is best observed, representing the first order rate constant for the decomposition of the complex, the consumption of hydrogen peroxide, and the degradation of ACTM, acetamiprid, as a function of the volumetric rate of photon absorption. As we can see, there is a linear range where the Kinetics constant increases with the availability of light. Okay? This is photolimitation. But in this range, an increase in the VRPA does not increase the rate constant, light saturation. So we proposed a kinetic model, a very easy kinetic model. You can understand it very fast. Okay? But in this kinetic model with 16 reactions, I'm not going to tell you every one of the reactions, only that ion precipitation and neutral pH and the presence of bicarbonate as a scavenger of hydroxide radical has been taken into account. Okay? This is a visual description of the model. And here we have the 16 rate law equation. To solve this system and to obtain the kinetic parameter, we use the hypothesis of perfect mixing and batch mode operation. And we solve the system with MATLAB. 3 of the kinetic parameters were taken from the literature. And here we have the parameters. I'm not going to explain you how to reach this. You have another talk later. But only to show you how the model is able to reproduce the experimental points, the experimental results, for different liquid depth and different irradiances. So the model works. Once we have the model in the stir-tank reactor at a lab scale, we need to validate the model, following the lesson by Professor Marugan. In this case, the model was validated in a raised boundary reactor with 5 centimeter liquid depth. in 2 different seasons, in winter and spring, with different temperatures, with different irradiances. Okay? And we can see how the model is able to reproduce again the experimental results. Okay? So that the model has been validated. We started with lab scale experiment, and now we have pilot plant scale experiments. Okay? But we are still working with synthetic wastewater and with a model contaminant, acetamiprid. What was the next step, or what should be the next step in every research we can carry out? Is the design of a reactor with real wastewater, to treat real wastewater. Okay? In this case, we worked with 5 different wastewater treatment plants along the Mediterranean coast, 3 of them in Almería, 1 of them in Alcoy, another in Girona. The 5 real wastewater were completely different, and we studied the performance of the photophantom process with this real wastewater. Okay? We found that the photophantom and neutral pH with iron 3 DDS remove the micropollutants effectively, regardless the water composition, and that an 80% of the micropollutant can be removed after 15 minutes of treatment with the 5 real wastewater effluents. That's the common results. We have little differences. One of them important, other not. But the main research is this. Okay? And we paid attention to 3 contaminants: gabapentin, orthodismethyl venlafaxine, and orthodismethyl tramadol. Now we want to apply our kinetic model obtained with synthetic wastewater with a model pollutant to the real wastewater to real pollutants. Okay? So we used the same model, and we changed the reaction rate, the rate law corresponding to acetamiprid by the 3 reactions for the 3 selected real micropollutants. Okay? And we fit the model to the 5 real wastewater, and here I show the results for 2 of them. One with a high level of contaminant, and another with a low level. Okay? And we can follow, because these results are in the Raceway reactor at pilot plant scale. The irradiance, UV irradiance, the photodecomposition of the iron 3 DDS complex, the consumption of hydrogen tetroxide, and in this case, the removal of ortho-dimethyl tramadol, dimethyl tramadol, one of the micropollutants. These results are for, I think, 5 centimeter liquid depth. And here we have the other 2 micropollutants. So, as we can see, the model was able to follow the removal of real micropollutants in real wastewater effluents. The model obtained with synthetic wastewater. Ay, perdón. ¿Qué ha pasado aquí? Disco mal expulsado. Okay. You. I pay you. Yes. It was not enough. Yes, but I can start again, please. go to 25, perhaps. It's no, not 22, 23. Okay, here. Who remember the presentation, the very nice presentation by Professor Esplugas? You. Who said Professor Esplugas? Answering my question. It was a prepared question. When I asked him about the future of advanced oxidation processes. Louder. Continuous, no? To reach large-scale implementation, we need to work in continuous flow. Okay? So, all the presented research were in batch mode, but we need to follow the reactor design, okay, with continuous flow, because we need to treat large volume of water. And the treatment time is very short. It's around 20-30 minutes. Okay? So, the next step in this study was the continuous flow operation of a Raceway pump reactor with real wastewater to remove real micropollutants. Okay? We worked with two different reactors with 5 and 15 centimeters, but here I'm going to present only results with 5 centimeters. 5 minutes, no? The treatment started with a batch operation for 30 minutes, and then the continuous mode operation started, and we worked with two different hydraulic residence times. 15 minutes for 2 hours, and next 10 minutes for another 2 hours, okay? Increasing the flow rate in the reactor, we decrease the hydraulic residence time. We wrote, you can read very fast, the mass balances of the model for continuous flow operation, and these are the predictions of the model for the operation in batch plus continuous flow. Okay? For instance, the model can predict the photo decomposition of the complex in batch, and next in continuous for the two hydraulic residence time tested. As well, the consumption of hydrogen peroxide and the removal of the 3 selected micropollutants. So, the model is able to predict the continuous flow or the behavior of the reactor in continuous flow. So we can use for the design of the reactors. In this sense, in this picture, you have, as a consequence of the application of the model in continuous flow mode, the variation of the treatment capacity of the reactor expressed as the cubic meter of water that can be treated per square meter of reactor and per day, as a function of the liquid depth of the reactor, and the hydraulic residence time, the style line. And we need to take into account, we started the presentation in this sense, for the design of the reactor, the objective of the reactor, of the treatment, okay? So the objective of the treatment, the removal of the micropollutants, can be 60% of the present micropollutant, 17 or 80. In the case that our objective is the removal of the 80% of the micropollutant present in the wastewater, we can work with a liquid depth of 20 centimeters, with 30 minutes of residence time, and we reach a maximum treatment capacity of 4 cubic meters per square meter per day. Okay? So, this is not the design of the reactor. Javier Marugan said, the design is to say how large is the reactor. Okay? The size of the reactor. How we can obtain the size of the reactor? Taking into account the flow rate we want to treat. Okay? In this case, for instance, if we want to treat 400 cubic meters per day with a treatment capacity of 4 cubic meters per square meter of reactor and per day, we need 100 square meters of reactor. Okay, so we reach from the basics of modeling the sizing of the reactor. Conclusion. The kinetic modeling of a photochemical process allows to calculate the treatment capacity and the reactor surface as a function of the reactant concentration, the liquid depth, of course, the residence time in continuous flow, the irradiance, light variability, and the last one, the target of the treatment. Thank you very much.